For the first type of addition reaction, we will learn the addition of two hydrogen atoms across an alkene. In this type of reaction, called hydrogenation, the regiochemistry will always be irrelevant, regardless of what alkene we use, since we are adding two identical hydrogen atoms. The hydrogen atoms that were added here are not explicitly shown. Remember, hydrogen don't need to be drawn in bond line drawing, so you should be able to see them even when they are not drawn. Stereochemistry for hydrogenation is always thin. In order to understand this, let's take a close look at how the reaction takes place. Notice first the reagent that we use to accomplish a hydrogenation reaction. A hydrogen molecule with a metal catalyst. A variety of metal catalysts can be used, but platinum catalyst is by far the most popular. The hydrogen molecules interact with the surface of the metal catalyst, effectively breaking the hydrogen-hydrogen bonds. This forms individual hydrogen atoms adsorbed to the surface of the metal. These hydrogen atoms are now available for addition across the alkene. The addition reaction begins when the alkene coordinates with the metal surface. Surface chemistry then allows for the following two steps, effectively adding hydrogen and hydrogen atoms across the alkene. Notice that both hydrogen atoms are installed on the same side of the alkene, giving a syn addition. Let's now practice. For each of the following reactions, let's draw the expected products. For the first example, these reagent here will add two hydrogen atoms across the double bond. We do not need to worry about regiochemistry because it is always irrelevant since we are adding two identical hydrogen atoms. And stereochemistry is always thin. So we can imagine adding the two hydrogen atoms from above the plane of this alkene here to get this product, or from below the plane to get this product here. To determine whether stereochemistry is relevant in this example, we must ask whether we are creating two new stereocenters. In this example, we are not creating two new stereocenters. In fact, we are not even creating one stereocenter, because if you examine each carbon here, you can see that it is attached to two hydrogen atoms. And actually, these products are identical, because if you take this product here and you flip it and then rotate it 180 degrees, you will obtain this product here. So there is only one product here, and for this reaction, we will get this one. For the next example, remember, regiochemistry is always irrelevant, and stereochemistry is always thin. So this will give us these two products here. And here again, we are not creating stereocenters, and so these two products here are identical. And finally, for the last example, if we add the two hydrogen atoms in a syn addition, we will get these two products. So this one here with the hydrogen atoms being added from above the plane of the alkene, and these two here added from below the plane of the alkene. Now let's determine whether stereochemistry is relevant or not. Let's first begin by rotating this compound here, like this, and compare it with this one here, and see if we are creating any new stereocenters. For this carbon here, and this one here, we are not creating a new stereocenter because each one of them is connected to two hydrogen atoms. However, for this one here, it is connected to 4 different groups. And if you look carefully, for this compound, ethyl group is on a dash and methyl group is on a wedge. And here, methyl is on a dash and ethyl is on a wedge. So here we are creating a stereocenter, and the configuration here is reversed. So these two compounds here are a pair of enantiomers. So for this reaction, we are creating two products, a pair of enantiomer. This product here with its corresponding enantiomer.